So let's now go look at the general definition for what it means to be an eigenvalue and an eigenvector. Suppose we have a square matrix, an n by n matrix. A scalar lambda is called an eigenvalue of A if there is a non-zero vector x so that A times x equals lambda times x. This is the same thing we just saw in the example, but lambda in the example was 1. The vector is called an eigenvector corresponding to that eigenvalue lambda. Now this idea eigenvalue, it harkens back to a really old, like many years ago, 200, 300 years ago. But there's a disconnect with people who say it's an eigenvalue, so we want to call it E. And that's because a while back, they were also called something else. They were also called in other parts in the world, latent values. And because of that, we use lambda for latent for our eigenvalues. Now you need to know then, how can you verify that a certain vector is an eigenvector? It's incredibly easy. All you do is just check, take the matrix times your vector and see if you get a multiple of the original vector. So here, for example, if I were to just take the vector, the matrix 1, negative 1, 1, 6, 0, and I multiply it by the vector 1, negative 2, just doing the multiplication would give you a negative 3 and a 6. And notice how that is negative 3 times the original vector. So then by definition, then this vector 1, negative 2 is an eigenvector for A, and that's corresponding to eigenvalue negative 3. So it's really easy to check if something is an eigenvector. You just literally multiply the matrix by the eigenvector and see if you get a multiple of that vector. The multiple then must be the eigenvalue. Now, suppose though that you have a known eigenvalue and what you want is the eigenvector. So notice that the equation, if there actually is an eigenvector for that eigenvalue, that means then A times X equals lambda times X. So let's just manipulate that equation, much like you saw me do in the application. So then notice you can rewrite the right-hand side as lambda times the identity matrix times X. But then you can bring everything to one side, and using matrix multiplication properties, you can factor out the X to get the equation that the matrix A minus lambda times I, that's a matrix, in this case right now, probably 2 by 2s, times the vector X equals 0. But since the vector X solves the equation of something, the matrix times X equals 0, that means X is in the null space of that matrix. So since we know that X is a non-zero vector, then by the following our equivalence, that means then there's more than one solution to this particular equation, this particular homogeneous equation. So by the following equivalence, that means the null space is non-trivial. So it's not just a zero vector. There's more in it. So the eigenvectors corresponding to an eigenvalue are always the non-zero vectors that are in the null space of A minus lambda times I. A times lambda times I. So that's really, really nice and easy way to figure out what the eigenvectors would be. I'll go over a couple examples. So let's say I want to know, give me one eigenvector to this matrix corresponding to the eigenvalue of negative 2. You might also wonder, how do I know that negative 2 is an eigenvalue? You'll see as we do the work how you know at one point that there has to be an eigenvector. Well, and that should be A times A minus lambda times I. A minus lambda times I. So then in order to find out the eigenvectors, I know the eigenvectors correspond to the null space of the matrix A minus lambda times I. So I'll just replace the A, I'll replace the lambda, and I'll just multiply that out to get, there's the matrix. Now I want to know then, how do I know that lambda here is actually an eigenvalue? Well, but if you look at that matrix, you'll notice that the rows are multiples. Since the rows are multiples, that means they are linearly dependent. So by the following our equivalence, the null space of that matrix is non-trivial. So we now know then by definition that, or by a result I just gave you, that -2 has to be an eigenvalue, and there has to be at least one eigenvector that goes with it. All we have to do then is to solve the system of this matrix times 0 times x equals 0. So then let's just write down the corresponding augmented matrix for that system and row reduce it to get this particular augmented matrix. So then if x is x of 1, x of 2 is an eigenvector for lambda equals -2, that would then mean that the components of that vector x1 and x2 would have to satisfy the equation x of 1 plus 1/2 x of 2 equals 0. So we know how to write null spaces, how to write down the solution space for the null space. You just go ahead and replace the vector, the x of 1 in that vector, with what equal to because of this equation. And then you can rewrite that as some multiple then. That's this part right here. That's the free variable part. Some multiple of the vector -1/2, 1. All we need then is 1. So if you want a eigenvector, a single eigenvector would just be -1/2, 1. That's one of them. But there's many others. You could choose x2 to be anything you like, as long as it's not 0, and you would get another non-zero eigenvector. So there isn't one eigenvector for the eigenvalue -2. There's an infinite number of them. Now, that brings up something else, though. It winds up being, though, that the solution set, all the possible eigenvectors for an eigenvalue, correspond to all the vectors in a null space. But we know from a previous lecture that null spaces are subspaces. They're subspaces of Rn. So then for every single eigenvalue of a matrix, of a square n by n matrix, that corresponds to a certain null space of A minus that eigenvalue times I. And we know that that null space is a subspace. So we're going to give it a name. We're going to call it an eigenspace. So the eigenspace is denoted as E sub lambda. It's simply just the null space corresponding to a certain matrix, A minus lambda times I. So as an example, I'll show you what I mean. Let's go ahead and find the basis for the eigenspace for the matrix for the given eigenvalue of 6. Again, you're probably wondering, how do I know 6 is an eigenvalue? That's coming in future sections. We can't do it in general yet, but we can do it for 2x2s, just not yet. So then if this actually is an eigenvalue, that means then A minus lambda times I, that matrix, which is in this case, A minus 6 times I, because the eigenvalue is 6. If you look at that matrix, it should be something that has a non-trivial null space. Well, I did the subtraction for you here, then I instantly row reduced it, and notice that there's only one non-zero row. So the matrix A minus 6 times I has a rank of 1. So that rank is not 3, which means that by the following equivalence, that the null space of this matrix is not 0, not 0. So I now know that null space is not 0, and therefore 6 had to have been an eigenvalue. So I want to know this time a basis for the null space, a basis for the eigenspace. To find the basis for the eigenspace for 6, I'm going to go and look at the corresponding row reduced echelon form and notice that whatever that eigenvector is, it has components x of 1, x of 2, x of 3. But by looking at the row reduced form, that has to solve those components, x of 1, x of 2, x of 3, must satisfy the equation that x of 1 plus x of 2 minus 2x of 3, that would equal 0. Because remember, we're looking for a null space, so it's this matrix times x equals the 0 vector. That's why it equals 0, man. So because of that one equation, that means that in the equation, x2 and x3 are free, x1 is a leading variable. So I can then take the eigenspace, being the set of all vectors that are the solutions to that set, that space. I can then rewrite that, take the x of 1 out and put in its place what it's equivalent to. And then I can rip that part of vector apart in terms of the free variables x2 and x of 1. But then you'd notice that this is just a set of all particular linear combinations, and that's a span of 2 vectors. We know the span is certainly a subspace. And from work you saw before, these 2 vectors here they form the basis. They form a basis for this particular eigenspace of E sub 6. It's pretty easy.